Hi everyone, we are Franca and Fabian and a cat, and we'll talk about graph neural networks for outerplanar graphs. So let's look at these two graphs which represent molecules. If you look at them, you can see they're obviously different graphs. And as many of you probably know, these two graphs are 1WL equivalent, which means that if you take a message passing graph neural network, it's going to give you the same embedding for the two graphs, which also means an MPNN is going to make the same prediction for the two graphs. And of course, this is not something you want, which is why people have come up with more and more expressive GNNs that are unfortunately also more and more inefficient with respect to runtime. Okay, so now if you've taken any machine learning class, the first thing you will have heard is look at your data. So now let's look at that. Here you can see molecules from popular molecular benchmarks, and what you can see is that they can all be drawn in the plane without crossing any edges. This means that these graphs are planar. And if you look more closely, you can also see that all of the nodes in these drawings are on the outside face, which means these graphs belong to the class of outerplanar graphs. And what we do in our work is we focus on exactly these graphs. We focus on outerplanar graphs, and we proposed a preprocessing that takes an outerplanar graph, maps it to another graph, such that if you then apply an MPNN on these graphs, the MPNN is going to be maximally expressive. And this transformation is called CAT. And CAT makes use of another transformation we'll call CAT star. And now Franca is going to talk about that.
So when you think about outerplanar graphs, basically the most difficult parts of them are biconnected components. And because it's outerplanar graphs, they are biconnected outerplanar components. And CAT star basically focuses only on these biconnected outerplanar components, which we call blocks. And what does a block look like? Well, basically it looks like something like the graph on the left, where you have some cycle and you have some edges in between, which we call diagonals. And what CAT star does, it takes this graph and it transforms it so that Weiss-Bell-Lehman or message passing neural networks can distinguish all of those blocks. And CAT star transformation is based on a very old result from the 1980s by Colburn and Booth. And what they found out is that because each block has a unique Hamiltonian cycle, you can basically encode the whole graph into a so-called Hamiltonian adjacency list sequence. And this uniquely identifies the biconnected outerplanar graph. So what we do is we try to encode this sequence into this transformation. So CAT star basically copies the graph and we then direct each edge in each direction of the Hamiltonian cycle. And for the diagonal edges, we direct them in both directions. And then in the edge labels, we encode the distance of the nodes that the edge belongs to on the Hamiltonian cycle. So for the edges that are on the Hamiltonian cycle, it's basically the distance is 1, because the nodes are neighbors on the Hamiltonian cycle. And for the diagonals, using only edges of the Hamiltonian cycle, the distance will be larger, of course. And we encode these distances in both directions. And this way, using this transformation, MPNNs can distinguish all blocks. So how do we now get from only blocks to all outerplanar graphs? Well, this is what CAT does. CAT first applies the CAT star transformation to all of the blocks of the graph. So in the graph on the left, we have these 3 triangles, and we apply CAT star to each of those. And then basically we use we add all of the nodes that and the edges that are not part of any block or that are in more than one block. After that, because while using CAT star, we basically created 2 copies of each node in blocks. we then connect those representation using pooling nodes. And then for each of those of the blocks, we add a node, a block pooling node, to basically connect all those pooling nodes. After that, we still are left with some connections that were in the original graph, but that are missing now. So we might have some nodes that appear multiple times in CAT, and we connect those. And after that, because now the graph might have a much larger diameter, we add a node that connects all of those block pooling nodes we added earlier, just to make the diameter more manageable. And this would not be necessary for the expressivity, but for in practice it's quite useful. And this way we can transform the outerplanar graph in linear time to make it distinguishable by MPNNs and by Weisberg-Lehmann.
So yes, CAT has some very useful theoretical properties, and it can also generate graphs like this that look like a cat. So besides theory, we also tried this in practice. So what we did is we took some molecular benchmark data sets and some MPNNs, and we compared them with each other. So we compared each MPNN against an MPNN plus CAT. And what we see is that on many data sets, CAT gives you a clear boost in performance. So it's not only nice theoretically, it also seems to work well in practice. So now, to sum up, what we did is we looked at a very specific class of graphs. And the cool thing about this is that this then allows you to achieve very strong expressivity results without a blow-up in the runtime. And yes, what we did is we came up with the CAT transformation, which transforms outerplanar graphs in linear time and ensures that MPNNs are maximally expressive on these graphs. And that is it. Thank you for your attention.